So it is my great pleasure to introduce Roxanne Springer from Duke University. She's going to give 101st Theoretical Physics Colloquium in this series. She received her PhD in 1990 from Caltech in California. She was a visiting assistant professor at the University of Wisconsin in Madison for 2 years before getting an assistant professor position at Duke University in 1992. Since 2012, she's a full professor there. She received some honors and awards over the years. In 1998, Robert Cox Trinity College Distinguished Teaching Award from Duke University, Moore Distinguished Scholar Award in 2016 from Caltech, and she became an elected fellow of the American Physical Society in 2017. She's very active in professional service. Between 2010 and 2014, she was chair of the Southeastern section. She was a member of the executive committee on Division of Nuclear Physics between 2015 and 17, chair of the NP LES program since 2020, and a co-chair of the NP Diversity, Equity, and Inclusion Committee since 2021. Her interests include weak interaction, quantum chromodynamics, fundamental symmetry violation, nuclear and particle physics, many topics in those fields. And today she will be talking about using large NC to order nucleon-nucleon interactions. And with that, I'll give the microphone to Roxanne.
Thank you very much, Igor. And as we're discussing, I really do appreciate that you've taken the initiative to fill this need of the community under the COVID protocols to make sure that we are still able to meet each other in a scientific space. I've definitely enjoyed attending these talks myself, and appreciate that they're also archived so that people can consult them later. I want to thank you also for inviting me to do this, because it's somewhat of an experiment for me, that in the context of writing this review for annual reviews of nuclear and particle science, along with Thomas Richardson and Matthias Schindler, one of my tasks is to try to come up with a way of ordering the explanation of how to do this, and I've made the title a little bit more explicit, using the large number of colors limit of QCD to find the relative sizes of nucleon-nucleon interaction contributions to a given process. So my goal, and I hope that through this talk, it's going to help us in writing the review to think through the best way to provide a roadmap for people who essentially want to walk in with their set of operators, whether it's a Lagrangian or a potential, and walk out knowing which ones, at least dictated by the large NC approximate symmetry of QCD, would be the dominant contributors to a given process. So we'll talk a little bit about why one might want to do this. And then I'll go through the elements, and the challenge is that each of the elements a little bit depends on the others, and so it's not really clear to me at this point what the most effective way is of presenting them. I should also say, by way of disclaimer, I've got friends in the house, in the virtual house, because I've been suffering from episodes of vertigo. And so I guess we get to see whether anxiety about having a vertigo attack may induce a vertigo attack. We'll take this measurement, and if things go south or if I go down, then there are people who will be able to step up and take my place, and at least hopefully give you a sense of what it is we're trying to do here. So I am just going to talk about the nucleon-nucleon part. If you want to look at the three nucleon interaction kind of hierarchy that NC suggests, then I would recommend starting with the Phillips and Schott article and a number of papers that have been spawned from that. All right, hopefully you can see my next slide here. So why would we want to do this? One, I think is kind of a theoretical, I don't know, prejudice, if you like, that progress in physics has always seemed to be a history of finding larger and larger symmetries, more and more unification, if you will. And in this instance, there's possibly the chance to be able to understand something more about QCD by looking at an extreme case of QCD. You might ask, who in their right mind would decide to use 1/3 as an expansion parameter? And it's a very good question. And what we'll see is that in many cases, especially if you stay within, say, a particular isospin channel, that the expansion is not just in 1/nc, the number of colors, but 1/nc squared. So that helps improve the situation. Most of you probably know that there are things that simplify as the number of colors becomes large, just from the point of view of analyzing Feynman diagrams, the way Chuft and Witten has explored. There are some that become dominant as NC become large. From a point of view of applying it to particle physics, we know that as NC changes, we're going to go from a symmetry that's dictated by SU3 to something that is much more constrained, SU of this much larger NC. And the hope is that for theorists, if there are no other guideposts, maybe because you're talking about a physics beyond the standard model for which there is no data, or something that has to do with non-perturbative QCD, which after all has to be very well understood before we can start to understand signals above that background, if you like, and begin to be sensitive, extracting physics beyond the standard model, then this is a way to help give us at least some information about what it is that people might want to pay most attention to. So when I talk about high order calculations here, I'm of the mind where some of these higher order calculations, you'll have just a gazillion operators and very little constraints on them. And by exploiting this enhanced symmetry that QCD gains as the number of colors gets large, then you can do something to reduce those number of operators. That's the idea. From a more practical point of view, and we actually saw this when it comes to some of these very, very challenging low energy parity violating measurements. These are very, very tiny signals, very, very expensive to measure. And if we can provide some guidance as to which effects are apt to be largest, then this can help to guide experimentalists about what to focus on first. And when it comes to the simulations, whether it's a lattice simulation, whether it is, I'll stop here to remind people that since sort of 2016, a number of workshops at the KITP, at the INT, at Mainz, have really started to formulate this process whereby we want to calculate on the lattice some parts of QCD, and by a separation of scales, then match that onto an effective field theory, match that onto with the informed parameters, whether it's an expansion in 1 over the large quark masses or expansions in small quark masses over the chiral symmetry breaking scale. And of course, here I'm advocating including the large NC. NC itself as an expansion parameter, 1 over NC as an expansion parameter, and then step from that to mini body simulations to address how it is that we can see QCD driving the physics of these larger nuclei, especially important when some of the larger nuclei can amplify effects, or when they're the ones that are being used to search for dark matter, for example. And you'd like to know, in order to optimize those codes, which of the QCD inputs are the ones that are apt to be most important. So that's the goal of why it is one would want to use NC to attempt to establish a hierarchy of operators. So you have a new particle, one or more, new symmetry, new idea, new interaction. And so you walk in with a bag of interaction. And this could be in the form of an interaction Lagrangian. So you'll have a set of low energy coefficients, C1 through C whatever. And these may or may not be ordered already by some other power counting that exists in your theory. From the operator point of view, you've got creation and annihilation operators, whatever Lorentz structure is necessary. From a potential point of view, what you've got are these low energy coefficients, each multiplying all the possible structures that might contribute, that might give rise to the process that you're interested in. And what we want to do is to provide a set of steps so that you can determine amongst all of these low energy coefficients, which ones are larger, expected to be larger than the others, over and above whatever power counting and ordering and hierarchy might already exist because of another parameter. Some of them will be equal to each other because that's what an enhanced symmetry does. It restricts the number of possible independent low energy coefficients. And then you'll see that if you want just the leading order in NC observable, you might have a function of a very few of these low energy constants. And then you can proceed from there, whether making that calculation at leading order, which, in the absence of any experimental data, something to 10% or 30%, might be really, really helpful, or wanting to get more accurate still and doing the higher order corrections in the 1/n NC expansion. So these are the elements, and I'll tell you what they are and then go through establishing how they are both justified and applied. So one thing to be conscious of is that when you walk in with your bag of interactions, you may need to do more work on those interactions before applying these techniques, or at least be very mindful that the basis that you are using, it's likely a minimal basis, because who wants to do more work than they need to do? But if you use Fierz transformations in order to reduce the number of operators, then this may be a problem when it comes to invoking large N scaling. And you might have to back up. I mean, these days, in fact, I would say instead of going to just a completely overcomplete set, which means that you just write down all possible operator structures and work with those and large N count those and then figure out which ones are most important. You can also start with the back end and kind of create the operators that are largest in NC that will contribute to your process. But that's kind of a choice as far as how to proceed when you arrive with your set of operators. Next, the spin isospin that is contained, the content of the spin isospin that's contained in each of these operators is going to have an impact. It's going to scale in some way with large NC when you take a nucleon matrix element. It's really important because I think a lot of the analysis that's done is done on the operators in isolation. But a really critical caveat is that these operators can't be applied to just anything. The tools we'll talk about really are directly related just to nucleons, because it's the nucleons that have such an interesting change in character when the number of colors changes. From there, to talk about nucleon-nucleon, which is as a scattering or an interaction involving an external current, for example. That's where we go from the single nucleon matrix element counting to the scaling within C, the counting within C of the two nucleon matrix elements. Another important element is to figure out the source of the momentum in the operators. So typically you're going to have some derivatives in your operators or some momenta in your potential. And you need to have an understanding of from whence it comes, because that has an impact on how that momentum will scale with the number of colors. Also influencing the counting of any contribution is the number of coupled pions. These are derivatively coupled. There is a known scaling with the large number of colors that the pions do couple with the nucleons, and that's going to affect the overall impact of how that interaction will manifest in the process you're interested in. I want to make sure to emphasize that these low energy coefficients are not themselves observables. They do have a subtraction point dependence. So it's really, really important that you don't kind of grab a bag full of low energy constants from one theory, especially if they have and give it to another theory if they have different degrees of freedom, or there's a mismatch in subtraction point dependence. That's just going to give you nonsense. And I'll illustrate some examples of that subtraction point dependence and the impact that it has. There's also a very interesting issue about the delta intermediate state and being explicit about including that, and that is some work in progress that's I may allude to. All right, so in order to figure out how these operators, terms in the potential, scale within C, we need to know what a nucleon looks like in the case where the number of colors is large. So we've got two things, well, got many things. We've got at least two things. One is that the group theory, and the other is the imposition of the Pauli principle, meaning that all of these quarks, no matter how many colors there are, all of these quarks are spin 1/2 objects. And so they need to live in a wave function that is the nucleon in a state that is anisymmetric under the interchange of any two quarks with all of the quantum numbers that it needs to label it. And that's easiest to analyze by looking at a product wave function. So you've got the color degree of freedom, and with its own interchange symmetry, the spatial piece of the wave function, the spin piece, and the isospin piece. Of course, if we want to have a fermion, then as our nucleon, then we need to have an odd number of colors. And furthermore, if we want to have a singlet in the color degree of freedom, so that we actually have a physical object we can hold in our hand or count in a detector, then we're going to need to build the nucleon with as many quarks as there are colors, because that's the only way you get a singlet. When it comes to three colors, this is well known. If we call them blue and green and red, then you can see that there is a singlet here, and we do have complete anti-symmetry amongst every pair of interchange. So if I take this first one, BGR, I see that switching the last two, or the first two, or the first and the third, all have creatures in the wave function that flip the sign. And so it's established that indeed we have that anti-symmetry. If I increase the number of colors to 49,001, then I'm going to need to have a nucleon that has 49,001 quarks. And the way that I create the singlet is listed as in terms of this Young diagram here, where we have the total anti-symmetry imposed by this column of boxes. And what's nice is that once that is taken care of, it can kind of be removed from, this is going to be the ground state. So I'm going to be thinking about spatial wave functions that are symmetric under this interchange. And so the color degree of freedom has fixed for me this anti-symmetry. And what's left is that I can go to now a set of so-called bosonic quarks. And really, literally, they are bosonic. It's important when you talk about the ability to reduce the number of possible operators that are in the QCD, if you like, matching that we'll do, that indeed these are actually obeying commutation relations. That's important for the ability to reduce the number of operators to be dealt with. And so that's just dictated here by this row of bosonic quarks. So that's what we need to accomplish. And I want to go through this in some detail because it actually makes the scaling of the isospin operators within C, I think particularly physical. So if you start with just 3 colors, then you're all familiar with what this wave function looks like, and in particular, you can start with just the spin degree of freedom and do the spin and the isospin separately. So if you start with the highest weight and have all of these to just focus on the spin part for the moment, these spin up quarks. And if I do a lowering operator on this, of course I have to, this remains symmetric. And what I want, of course, is not, if I want the nucleon, I want the total spin 1/2, not the total spin 3/2. So if I lower this one, I've got the 3/2 total spin 1/2 projection. And what I need to get my nucleon is something that's orthogonal to that. But there's an additional, as we already discussed, constraint here, which is that there needs to be this total symmetry involved in the spin and isospin. So a way to sort of encode that is to actually separate out the isospin part. You can go ahead and symmetrize if you like that one, but that symmetrization is already going to be dictated and encoded by the spin part. So the way to read this is that the first flavor goes with the first spin, the second flavor goes with the second spin, etc. So this is distributed. And to look at all possible combinations, so here is the whole, 1/√18 normalized look of the wave function for n c = 3, and you notice, or I want you to notice, to focus on the fact that we only need to deal with one of these 3 sets in order to see what happens as the number of colors gets larger. Another way to describe this is to talk about the symmetrization after you have done the distribution of all of the flavor quantum numbers into the spin quantum numbers. All right, so just focusing on the relative weights, and no, I don't mean the group theory weight, I mean it's Gordon, but of the different components of the wave function, what you notice is that as the number of colors gets larger, you have more and more of an emphasis of this wave function on things. And now this is particular, we're applying it to a proton that is spin up. Proton that is spin up tends, as NC goes to infinity, to be made up of a whole bunch of up flavor quarks with spin up and down flavor quarks with spin down. And they're all matched up except for one. And in the extreme case, in C = 2m + 1, so you know that it is an odd number of colors, and this distributes itself by this now very extreme situation where you've got a mapping here, and I've drawn all the schematic of the NC number of quarks where the identification of the lines is listed. So what we see is that even though I can't calculate actually a non-perturbative matrix element, I don't know what the nucleon looks like in terms of all the quarks and gluons and the QQ bar bears and all the crazy stuff going on, but I do know that in this large N limit, we've got a dominance of a particular piece of the wave function, and that is paired up so that if I look, for example, if I want to look at a matrix element of, say, the number operator, Q dagger Q, and these are the bosonic quarks here, and the big N stands for a neutron or a proton, and the N with a C is the number of colors. I'm afraid there are some sort of font changes going on here, and of course, there are more N's around than one would like. But think about if you want to take a matrix element, then you'll need to drop this operator in everywhere, all of the quark lines of this nucleon. And just from the component of the wave function, what this wave function looks like, you can see that for the number operator, every time I drop this in, each and every one of these quarks in the nucleon is going to add coherently. So not surprising that it looks like it's going to scale as the total number of quarks, which is to say the total number of colors. Now, it's possible that other cancellations will occur, which is why there's this less than or about equal to that Dash and Jenkins and Vanaher talked about. But it can't be larger than that when it comes to scaling within C. This is also not to say that there couldn't be some other, crazy number. We'll talk about that later. Things that could destroy the scaling. But when it comes to or destroy the utility of scaling, but when it comes to the scaling, this is the largest it can be for NC. On the other hand, if I look at one of these Pauli matrices here, the tau being in the isospin space and the sigma being in the spin space, it's clear by looking at this wave function that as I add up, inserting this operator on the different lines, I'm going to have up, down, up, down, up, down, up, down, and everybody's going to cancel but one. And so that is a destructive interference, and we don't get this enhancement of the operator. The best it can do is to scale as one when it comes to the number of colors. And similarly for the spin case. And possibly more interestingly, we'll look at this spin with isospin situation where it's true that each of the spins is alternating back and forth, but it does so in tandem with each of the flavors oscillating up and down, back and forth. And so once again, there's the coherence. So this is the ordering. And what we want to do is try to utilize this ordering, this hierarchy, in order to find out what it is that our more complicated operators will do. So these are just some of the examples of it's a spin isospin structure that's coming into play. A few other elements are needed to bring all the steps together, a few more concepts, and one of them just has to do with, and I should say that when it comes to various quantity scaling with NC, there are different ways to do it, and people think about ways to consistently employ the different types of NC scaling, and so it's interesting. It's an interesting question, the extent to which particular observables will really force one realization over the other. But loop diagrams, or in particular this beta function, need to be finite as the number of colors becomes large. And in order to do that, that dictates how it is that the strong coupling constant or strong coefficient should scale in this pretend world, this enhanced symmetry world, where the number of colors is much larger than 3. And one impact of that we're going to need to use in order to figure out how it is that the presence of pions impacts the large N scaling of the interactions that go into our process is to look at this current correlator and notice that this quark loop can take any of the NC colors, and so that scales as NC. And the corollary to that, if that's going to be the amplitude, then the vacuum, the probability amplitude of popping a pion out of the vacuum needs to scale as the square root of the number of colors. And because this matrix element is proportional to the pion decay constant, that's what dictates the pion decay constant to scale as the square root of NC. And that will be used to count what happens every time a pion is encountered. The f pi appears, and one can use the scaling of the f pi in order to inform the scaling of the entire operator. Now, because of understanding this scaling of the strong coefficient, and this is work based on Kaplan and Savage, Kaplan and Manahar, they're the ones who looked at the the impact on a potential of this kind of scaling. Also really interesting discussions by Banerjee, Cohen, and Gelman about different ways in which you can take the momentum to scale with color. There are lots of interesting discussions. Oh, and also some discussion of the role of delta there. So those are part of a series of very interesting papers. And you see that if you think about scattering, a diagram such as this one, where I've got in one nucleon across the top, going into what's called N2, scattering with N3 that go also off into N4. And if they exchange quarks, then they're going to need to conserve momentum. So they need to exchange a gluon. But each of these gluons, as we've seen, is going to come with this scaling of G over the square root of NC. And on the other hand, the number of ways that you choose that is possible to invoke this quark exchange is NC squared. And so the whole thing goes as NC. And that is why conventionally there's this NC that goes out in front of everything. Another way of looking at it, I'll get to that in a moment. So what does all this notation mean? So the little n's, the little n prime, stand for the number of bodies. So if you've got a bosonic Q dagger and a bosonic Q, that's a one body operator. If you've got two Q daggers and two Qs, then it's a two body operator, and so forth. And the idea here, there is twofold. One is that because of the large number of colors, because of the massive number of quarks in each of these nucleons, you can factorize it and keep the N2 with the N1 matrix element and the N3 with the N4. And that means that the analysis of figuring out the impact of the potential will be dictated by the scaling that we've already looked at in the single nucleon matrix element, which is encoded here again. Okay, so we've talked about how it is that a spin isospin part of an operator can be enhanced or not when a matrix element is taken with a nucleon or two nucleons in a scattering situation. And we want to now formalize this, argue about why it is that those are the relevant matrix elements to think about. Why are those the relevant spin isospin structures? So coming back to this highly symmetric form of the nucleon, when it has so many of these quarks in it, the hypothesis is, and I think Witten has essentially proved when the number of colors is large enough, that basically what happens is that each of these quarks, if you like, these bosonic quarks, and you might you'll call it a quark, even though it might not be a conventional QCD quark, but it's existing in a mean field such that each of them separably sees the same sort of background potential. And that gives rise to this so-called Hartree, in the same sense that in chemistry, you think of a Hartree wave function and a Hartree potential that factorizes in this way. And at the same time, there's a Hartree Hamiltonian or maybe call that the interaction part of the Hamiltonian with this NC out front. And not only are there the spin and isospin structures, which now have this shorthand notation for each of these operators, the SI, where I is going to label the spin index, and A will label the isospin index, and then this operator here that has them both together. But this saturates the possibilities, with the understanding that this coefficient here, this V, can also have things in it that modify the scaling, and that can involve the momenta, and it can involve pions. As an example of how to do this is the strong interaction leading order when it comes to derivatives, where there's a scalar term, so in dagger in with in dagger in with a low energy coefficient that's labeled scalar, because that's what this operator structure looks like. And then the other possibility is that there is this tensor structure with an in dagger sigma I, where the summation is implied over the i's here. And if we impose this matrix element ordering that we just talked about, then I've got a scalar. I've got the unit here, this number operator along, I'll call this because of the factorization, nucleon line 1. And another number operator for nucleon line 2. Whereas for the scalar case, this is just symbolically indicated by this spin operator. And applying the spin isospin scaling rules, this gives me this low energy coefficient with NC squared, because each of these unit operators gives me a factor of NC. Each of the spin operators scales is NC to the 0. And so in mapping this, so in this instance, the Lagrangian you're walking in with is this 2 operators, one with the scalar and one tensor, and matching that to this large NC Hartree form. The matching is done by absorbing the counting in the coefficient. So that is how it comes about when you match to this Hartree form. Now that this scalar low energy coefficient now goes as NC, because I've got the overall NC taken out and I've got the NC left over. And here for the, oops, this is not supposed to be scalar, it's supposed to be tensor. Sorry, typo here and here and here. I need to fix that. The tensor operator then with the factor of NC extracted as scales as well. So notice a couple things. One is that you came in, you walked in thinking, I've got here 2 operators, meaning 2 LECs that I need to fix via experiment or calculate on the lattice or whatever. And then I find out actually that if I take large NC into account, they're not only ordered, but their difference is not just 1 factor of NC, it's 2 factors of NC. And this it happens over and over again in these channels that have different isospin. When it comes to the momentum dependence, the way to think about this is to try to figure out whether the velocities that come about when taking these matrix elements, whether they come about because they're just a canonical momentum exchange, or whether they're actually the result of a relativistic correction. If you want to think about the spinner and doing an expansion in the momentum over the nucleon mass, well, the nucleon mass scales as NC, because what we've got here is just the number of quarks, and each of them is multiplied by the individual quark mass, which could be very tiny, but here you've got an infinite number of them. And so because the mass of the nucleon scales within C, if you've got a momentum that is coming through a velocity that is a relativistic correction, then this is going to kill you by 1/nc. So this is one of the examples of where, when you look at the spin isospin structure, it's like, okay, this is as large as it can be, but there are also other things that could reduce it. And that's good, right? Because the more it's reduced, the more it gets shuffled to higher order. And that means that at the lower order, you have fewer operators that you need to worry about. So here's the encoding of the so-called the P minus linear combination, which scales as NC to the 0, and then the one that comes through from this relativistic correction that picks up an inverse factor. I want to talk about Viertzing. So I mentioned at the very beginning that when you walk in with your set of operators, you need to wonder how you got them. And I've actually already done this, right? Because if I go back and look at the complete set of possibilities here, I've actually got an indagger in with indagger in. I've got something that looks, this is the tensor with the spin. I've got something identical, except with the sigmas replaced by taus. And then I've got the one with the g's in between. All of these I can write down. They are not independent when it comes to Viertzing. And so typically one just talks about these two.
Roxanne?
And it turns out that in this case, indeed, there isn't a problem for reasons we can talk about. But the fact is that
Roxanne?
yes.
We have a question here from Thomas Schaefer. He says, naive question, doesn't a binding momentum scale as NC?
Doesn't a binding momentum scale as NC?
I mean, that was kind of a naive question. So the mass scales as n, the binding energy also scales as n. Doesn't that mean that a typical momentum also scales as n?
Ah, okay.
So P squared over m is E.
Right. So if you look at what Witten does indeed have momentum scale as NC. And the idea behind that is, look, I'm staring at this potential and I want all of these terms to be the same order in NC in order to get, you know, what I consider to be a consistent a way of power counting. But the analysis that Kaplan-Savage, Kaplan Manahar, and Cohen Banerjee, and who was the other person, did show that, in fact, if you want to get consistency, if you're talking about taking matrix elements of a potential in a nucleon-nucleon scattering situation, you do not get consistency unless you scale as the momentum scales as NC to the 0. So it's a totally valid point that when you're trying to accomplish different things, it looks like you have to be in a different momentum scaling region. And if that makes you uncomfortable, it should. But it's one of those things where you try to be as consistent as you can be with what you're trying to do at that moment. And I guess this is really no different than being in different scaling regions. If you've got like potential photons, right, and you've got different V scaling for them in different regions, then that's what it is. Okay, so the trouble with the Viertzing is that in a Viertz situation, you're really just talking about something that is a mathematical identity. And so you'd be like, this is an operator. I'm just doing a mathematical manipulation. There's nothing wrong with that. I'll just go ahead and do that. And what could possibly go wrong? Well, what goes wrong is that you have to take into account that you're not talking about the analysis of these operators in and of themselves. It is the matrix elements of the operators. And that is where Viertzing can get you into serious trouble, because not only can it exchange these different momenta that scale differently within C. You know, whether or not you pick the initial binding one to be of a particular order or not, the relative is going to be different here. And also, if I look at just the 2 nucleon case, no matter how many derivatives, I can actually just eliminate isospin completely, and that's clearly not a complete basis, and I risk removing some of my higher scaling operators and hiding them in one that appears to be of less importance if I don't pay attention to the fact that living inside of it is one that's more important. So that's why one safe thing to do is to start with a overcomplete set that's just ridiculously overcomplete, all possible structures without doing any Fierz reduction whatsoever. An example of a process that illustrates almost everything but the pions of these concerns, steps, rules, if you like, is to look at low energy parity violation in the 2 nucleon system, and this includes when you gauge these the derivatives in the Lagrangian or the momentum in the potential external currents as well. This is all consistent. And what Gerlande did was to notice an important thing, which is that other places in the literature it was unclear how many independent low energy coefficients there actually were at a given order. And he went through and he pointed out, look, you know, you can do this Fierz, you can either start relativistically and then do the reduction, or you can start with non-relativistic. You all get this these 5 independent. However, if you just walk in with that, and the way to interpret this potential here, I've got one of these P pluses, so that's going to give me a 1/NC hit. The sigma 1 means that it's acting on nucleon line 1. Sigma 2 is acting on nucleon line 2. And if I look at just this first one and play this game, I've got my 1/NC from the relativistic momentum. I've got a spin operator on the nucleon line 1, but just the unit operator, nothing's happening in the other, and also there's no isospin going on here. And I've got 2 components. Oh, there should be a minus sign here, but okay, this is all just scaling. And you're putting all this together and pulling out the NC, you see that this would tell you that G1, and indeed going through the manipulations and imposing these set of tasks, gives you the following scaling for these 5 operators, which would apparently tell you that there's only one that is leading in both. In this case, it's a momentum expansion leading order. I need to have a momentum because I've got a P wave. This is parity violation. So the lowest order is an S wave to a P wave, an L = 0 to an L = 1 transition. And it would say there's only one. Life is dictated in this dual expansion of momentum and 1/NC by one coefficient only. But this is totally wrong. And the reason it's totally wrong is because this is a minimal set that was obtained by Fierzing without regard to how that might have been hiding the spin isospin that drives the most dominant dependence on NC. So instead, you can go completely non-minimal. These are all the possible structures. And these are also written down by Phillips and Schutt. And Smart and Schindler with the time reversal violation. And what we see is that with the counting this non-minimal set, or maybe more to the point, what you find out is that many of these, when you take the matrix element with a nucleon, you only get certain linear combinations. These are not all independent. However, what you notice that for this G1, where the scaling was so suppressed, as we saw in the earlier slide, when it was naively thought that that G1 was all there was, or that was the maximum scaling in the spin isospin structure. You see that in fact there is a dependence through the Fiertzing on something that scales here as in C. And so the correct scaling, when you don't fall into the Fierz trap, is that there's not just one leading operator in the dual expansion, but in fact there are two. Here it looks like there are three, but notice that G1 and G1 tilde, the largest in C scaling, these are actually related to one another. So this is an example of not only in the dual expansion being able to get rid of some of the LECs because some are larger than others, but also that some collapse because they are related to each other. And so that gives us the correct answer, which is 2. Leaving just 2 LECs for this system. I mentioned the pions, and we come back to how pions are included in the theory. Well, if it's chiral perturbation theory, then I am including them in an operator that has this nonlinear realization where the pions are in this, or if you like SU3, the 3x3 matrix, if you include the kaons and the eta. On the other hand, as we discussed before, this F pi scaling is the square root of NC from the vacuum decay constant. And we see that every time a pion appears, we have an inverse power of F pi. And so the pions also make the operator take a hit. Here is an example of an analysis of external currents, including zero neutrino double beta decay. And this is one of the operators. And you can practice if you like and see if you can apply these rules and predict what in C anyway says about how this low energy coefficient C2 with a bar over it, this is one of a list of many, actually how the leading operator scales, because again, you're matching it to this Hartree Hamiltonian and encoding the NC dependence in the coefficient.
Quick question.
Yes.
Was capital F the same as the decay constant little f pi?
Did I call it a different F before?
On the previous slide, there was capital F in the Lagrangian, and no.
Oh.
The pi, yeah.
Yeah.
That's the f pi 2, right?
Okay, that is the third typo. Matthias, will you write this down for me so I can fix these slides? And more importantly, the review.
Okay, no problem. I just wanted to clarify.
Thank you. Thank you for that. I appreciate it. All right. So you might want to ask how well this works. And that gets us into the interesting situation of subtraction point dependence. That whenever you're doing loop calculations, and in particular for this leading low energy nucleon-nucleon scattering, you've got to sum up a whole class of diagrams at leading order. So that's loops. If you're going to have loops, you're going to have divergences. If you're going to have divergences, you're going to have counterterms. And this means that you're going to have matrix elements that in order to have your observable independent of the subtraction point, you're going to have a coefficient that depends on the subtraction point. So that makes things a little tricky, right? It's unsatisfactory. You might like to have a large in scaling of your coefficient that does not depend on some random mu, but it is what it is. And when you match, that's what happens. And so we deal with it. And this simple example that I gave earlier to illustrate the method, you can ask, well, how about how well this works in real life? Well, in real life, what you measure are not the scalar and the tensor, but you measure the triplet partial wave and the singlet partial wave. And so mapping the scaling onto that would tell you that the scattering lengths of the triplet and the singlet are the same. That's what the large N result is. And clearly these scattering lengths are not the same. But this is not really telling you that the scattering lengths have to be the same. What it's telling you is that these LECs are the same at a given subtraction point. So basically what happens here is, the lore is that this unnatural scale is obscuring the large N scaling. But if I look at who this was, I think I referenced it earlier, Fleming, Meehan, and Wise. Yes. It talked about that it's not really the difference in the A's, but 1 over the difference normalized by 1 over the sum. And this is actually a better expansion than you might expect. And in any event, well, I guess we saw that actually it's not 30% corrections. It's more like 10% corrections because it's whatever NC squared. But basically to get this to be reasonable requires that your subtraction point, the place where you evaluate this low energy coefficient, has got to be relatively large, at least the pion mass large. Now, the fact that this is actually agrees with some other analyses done by Meissner and company, I believe, in the chiral where they actually have pions in it. So it's not a totally a new concept. If I look at 2 derivatives, I see once again that I've got this zone. I would predict these to be the same, and I see what actually the correction looks like experimentally, how close the effective ranges really are. So in this instance, if I think about an effective range expansion, it starts with the scatter length A, and the next term proportional to p squared is this effective range. I've got the 2 channels, the singlet channel and the triplet channel, and large NC tells you that these should be the same. And experimentally, this is what the situation is. If I want to have a 30% band or a 10% band, this is what happens. And the next slide, I think I have, yes, another prediction in the 2 derivative sector. So this is an example of p waves, because in 2 derivatives, if I have 1 derivative on the incoming channel and 1 on the outgoing channel, this is going to give me a p wave. And we see that leading order in NC, you'd think this was going to be 1, and experimentally it's 0.82. This is not terrible. This is about what you would expect from this kind of analysis. It's going to give you insight and possibly trends. These are not going to be hardcore predictions. We use NC when it's the best thing out there to give some guidance. If I look at what this has to say when we compare to existing parity violating measurements, so that I was using the leading low energy parity violation and including external currents as a way to illustrate these rules. And we have done the calculations to see how this compares to the experiments and the limits that do exist. And it actually does agree so far. This is here, instead of having the 5 coefficients listed either in the, I'll call it the Girondo basis, or the in-Dagger-in basis. Again, we've recast this in the more experimentally friendly partial wave basis, but that's just a difference in basis for expressing the operators. And the LECs absorb or inherit the large N scaling that came from the LECs in the other basis. And then you can extract what they are by comparing to the experimental result and the leading order calculation. an example that depends on just one of these, just because of the way the basis is chosen, is the famous NPD gamma out of Oak Ridge's SNS, and it indeed confirms that we've got something that is smaller in the channels that we expect it to be smaller. But there are a lot of error bars running around, as you can see, and so this is still we'll see, a work in progress. And here's just where I was looking, just playing around a little bit with these two coefficients that should be dominant in C, and what happens when you look at one of the experimental limits for a circular polarization of photon here in this breakup of the deuteron to NP. So, in conclusion, I have no idea what time it is because this is in full screen mode.
We're okay. We are okay.
Okay. I want to argue that this is can be a useful thing to do because, one, it can give you insight into the theory, and two, it can help guide other efforts, experiment, lattice. You notice in the parity violation, there was this delta I equals 2, a change in isospin 2 flying around. And that's something that I'm about to call it low-hanging fruit, but of course the lattice people don't. Basically, it's a clean signal on the lattice when it comes to not having all of these disconnected diagrams. So it's something that they could calculate and help confirm the large NC scaling. If they like, and also, of course, it's interesting because they have not just the ability, but it's not a bug, it's a feature of the looking at the heavier quark masses and hence the heavier pions. I mentioned already that when it comes to the spin isospin, that if there are other additional cancellations, other additional symmetries that are not dictated by the SUN, or the matrix elements that come from the baryons, then that would be a reduction. And on the other hand, just as in heavy quark effective theory, when you try to apply that to the charm quark, sometimes things go badly wrong because the charm quark, it's just not that heavy. And here, if you run into a situation where your expansion in parity violation, because there's more than one isospin channel, there you'll notice that the relative sizes is not an expansion in 1 over NC squared, it's actually an expansion in 1 over NC. So even though currently experiment actually agrees with the ordering that we find, it won't be surprising if that gets modified as the experiments reduce their error bars or as more experiments come in. It's really, really important to not, because I say this because I've seen it happen where people just sort of run across an LEC and they're like, oh, I need that one, I'll dump it in my theory. You need to be very, very careful about being consistent about running around with things that are not observables. Yeah, and just in general, I like that there's this additional tool in the toolbox, something else to expand in and look at the interplay between this expansion parameters and others. Thank you.
Thank you very much. Thank you for a nice presentation. We'll have time for some questions. So please raise the hand if you have a question, and we will go in the order of raised hands. To break the ice, let me start with a simple question. It's concerning the one tool in the toolbox, as you nicely put it. Well, every tool has sort of its specific role where it is most efficient and sometimes where it's the least efficient. So in your opinion, log-NC in application to nucleon physics, so what is its sort of the best place to apply and where it's probably the worst place to apply, so where it's unlikely to work well?
Very interesting question, partly also because as I alluded to, this procedure of trying to start with QCD and get zero neutron double beta decay out of some really heavy, germanium or something. That there are many things that can potentially go wrong, and not least of which is that at the moment, the cleanest, theoretically most well understood RG analysis is doing this on a pionless theory, on a theory without pions. Mm-hmm. And this has been exploited, I think, to good effect by Bira van Kolk and his collaborators, and the guy from like two syllables, short name and short last name, Jerusalem. Yes, thank you. Because they're taking advantage of the fact that you can do these lattice EFTs with heavy pions. Otherwise, you would say, heck, I'm not, I'm going to be sensitive in just some regular nuclei that you think about. I'm going to be sensitive to momentum transfers. I've got to have a pion degree of freedom in there, right? So that's when it comes to with the chiral situation, things are much more challenging because there's so much less control and so much less. Well, at the moment, for example, they in these calculations, they can't take their cutoff to infinity, which means that now I understand, practically speaking, you do what you can do, and there are really interesting results that come out of that community. But it's an open question being able to match these theories together. So that's where I would be a little bit worried about it.
Okay, good, thank you. Any questions from the audience? I do have a couple of questions, but I don't want to just be the only one asking. So anyone else? Well, I am interested in this, so I do want to ask another question then. Regarding the fierce reduction, frankly, I got confused. The reason I got confused is this: when you feared some operators, of course, you get different forms of operators, and naively from your power counting, it seems like they will be a mixture of higher and lower orders. Lower orders I don't really care about, but I'm sort of confused about the fact that you occasionally get higher orders, which means that after fearing, something becomes much more important than naively you've seen before doing so. So is there some sort of contradiction built in there? I'm really confused about that.
Okay, good. So basically, if you don't fierce, so the problem with fiercing comes in when you have used it to reduce your operator set before you think about what you're doing. Mm-hmm. Right? You've got all this freedom to choose whichever of these operators you feel like choosing, and you were doing it without regard to the NC scaling, because you were thinking about it in terms of just what this operator is doing mathematically and not the matrix element that you're going to be taking. So the easiest thing to do is when somebody walks in with a bag full of operators is to say, hang on a minute, just go back and reanalyze this and write your operators in terms of the spin isospin that you already know is going to be dominant. And then just count those. But if you
I'm confused, how can you tell upfront which will be the dominant?
So that comes about because of this known two structures that are dominant. And so if you go back and look at the let me see if I can find this again. Oops.
You did stop sharing though.
Okay. Okay, first, and then I share it, and then I do. So instead of just, walking in with all this exhaustive set of possibilities, you could walk in with like A5 minus, right? That one's clearly going to be dominant. A3 minus is going to be dominant.
And you're judging that simply from the spin isospin structure.
That's right. Because I see here that for A5, I've got on nucleon line 1, I've got both a sigma and a tau. So that's my G. And nucleon 2, the same thing. So that's as large as it can get. And same thing for A3 minus. I've got that G operator on both lines. You don't see I'll just unity here because it's mixing with S and P waves. Oops. Yeah. So, you know, if you hate yourself, you can just go back and have this huge overcomplete set and then do this reduction and then, you know, count them. But if you already have your eye on the ball and know where you're going, then you're going to choose ahead of time your a minimal set that will be easily compatible with the large NC scaling, just to make your life easier so that you don't have to worry about what operators you might have gotten rid of without paying attention to what their matrix element might be.
Okay. I think I'm starting to understand, but frankly, I have to think about this a little deeper, but thanks. Okay, I don't see any questions from the audience still. So I guess I'll use this opportunity and first thank you for a very nice presentation.